So welcome everybody. My name is Jeremy Gibbons, and I'm delighted to introduce my colleague Patrick Jansson, who is here in Oxford this term on sabbatical from Chalmers University of Technology in Sweden, where he's a full professor doing functional programming, programming languages, domain-specific languages, but in particular with applications to climate science, and collaborating with his wife, who's also here on sabbatical this term, plasma physics, as we're about to find out. Patrick and I have known each other for more than 25 years, a long time, and I'm looking forward to the talk. Patrick.
Yeah, thanks. Happy to see you here. I will talk about, as the title says, optimizing sustainable energy using functional programming. And I have got a little bit of a picture here on the left indicating one of the application domains, which is fusion plasma physics. So this is a schematic of a fusion reactor, something that hopefully will be able to create energy for the grid in the future. There's long-term research on that, also very close to us here. And on the right-hand side, it's a bit of an illustration of the more second part of the talk, when I try to talk about what happens with optimization, minimization, when you have multiple objectives, and then you don't get a single point as the optimum, but you actually get something called a Pareto-front, which is a curve. And this is a fake case, but inspired by the climate side. So you want to minimize emissions and spending, but not surprisingly, you can't minimize them both at the same time. So then there is a trade-off, and that can be illustrated with this Pareto-front. So hopefully, by the end of the talk, you know a little bit more about this fusion experiment example, you know more about optimization in different ways, and definitely a little more about the Pareto-fronts. Okay, well, we also got an introduction already. So I'm Professor of Computer Science at Chalmers University of Technology and the University of Gothenburg in Sweden. It's on the, well, I guess it's crossover from Scotland to Denmark to Gothenburg. I do programming languages, software correctness, and algebra programming, which is a nice connection because Jeremy is then leading the algebra programming work here in Oxford. So I'm visiting fellow now for until December 19, basically, physically here. As mentioned, I had a recent collaboration, a research project that we applied for together with Professor Tilde Philip, who's a professor of physics at Chalmers and also happens to be my wife, as mentioned. And it was about optimizing fusion then, using functional programming. And basically, I'm said in the title, sustainable energy, because, and I could be even more general, because this is sort of mathematics. It's multi-objective optimization. Here is the energy area, nuclear fusion, I mean, the energy source of the sun and so on. But we could apply it to almost any kind of optimization problem. So there is also a long-term collaboration in the background. So I've been working with the Potsdam Institute for Climate Impact Research since at least 15 years. Starting out with actually from the algebra programming side, because they had read the book Algebra Programming and they wanted some help in applying it to the real world. So they, for some reason, didn't contact, well, maybe they contacted Oxford as well, but they got in touch with me and my research group, and then we did some vulnerability modeling, sustainability science, and we tried to do verified methods for optimal decision making. And given that policy making is a rather messy field, you might be wondering what on earth can be optimal about it. But this is basically saying that if we have a model of the world, it's often probabilistic. So something simple model of what will be the outcome of a certain decision. And then say you have a number of decision time steps, 1 to 10, maybe once a year, you have to decide, should we go green or should we wait in some abstract sense? Then you can try to compute, if you have a reward function and a simulator for this, you can compute what are the optimal decisions to be made. And actually, it turns out you have to compute what is called optimal policy and not just the optimal decision sequence, because the world changes as you do these decisions. So you have to have a function from your current state to the decision. Anyway, this is all done in this side with the Potsdam Institute in the context of climate impact research. And I've inserted here a little aside, just to mention that climate impacts research is not the same as, but clearly related to climate research. So climate research is basically about understanding the climate system by itself. So ocean currents, atmospheric dynamics, radiation balance, ice cores, and so on. Human carbon emissions here is just an input, and the trajectory of the Earth system is the output, or maybe a probabilistic distribution of trajectories of the Earth system. Climate impact research, on the other hand, then also brings the humans into the system. And then clearly this will be a bit messy and uncertain. So the climate has effects on us humans, but more importantly, we humans have significant effects on the climate. So areas that are also brought in addition to the previous ones, are the economy, energy, land use, policy making, etc. So more uncertainty that's brought in here also means it's important to model uncertainty explicitly. So if we want to give advice to policymakers about the future, we have to be very clear on what kind of sort of error bars or what kinds of uncertainty do we have. And there are different kinds. There are the sort of uncertainty in the model, how you model the world, and uncertainty about if a decision will actually be carried out, and different kinds of uncertainties. We don't need as detailed climate models if you want to do this kind of simulations, because if we have so much uncertainty in the inputs, remember the climate research side will be able to compute the future trajectory of the climate given emission outputs. But if we're very unsure about the inputs, then it's a bit overkill to compute the trajectory with 3 digits of precision. So we actually can use rather crude climate models, but coupled to some models then about like economy and people's behavior. I should also mention that I don't know climate impact research that well. I mean, there are people who really do that as a topic. I'm a computer scientist. I have this application area, but it's not my core competence. Anyway, 2 main applications here that will be mentioned during the talk. First, the fusion thing. And I should mention, just as an interesting national and local connection, physical experiments, large ones, have been running here in the Oxford area for 40 years, the Joint European Torus experiment from 83 to 23. At Culham near Abingdon outside Oxford. So really, like, you can walk there. Now, well, yeah, you have to walk for a while. But it's compared to Sweden, it's pretty close, I would say.
Cycle.
Yeah, you can cycle there, yeah, sure. And then there is a new project. So this, I mean, the fact that that project ended doesn't mean that the fusion research in the UK is ending. There is a large project, spherical tokamak for energy production, STEP, which is supposed to put energy on the grid, I think. I'm not quite sure when and if this will work, but we've got colleagues also working on that project. So it's actually a rather hectic time in fusion right now, because for some reason, venture capital has sort of heard about fusion and started investing. So 10 years ago, there was very little sort of industry funding. And now the industry funding is much bigger than the government funding on the fusion side. So apparently somebody thinks that it might work. I mean, still doesn't, but I mean, work here in the sense of economy. I mean, we know how the physics work, and then the sun is definitely shining. So fusion is going on continuously there. I mentioned these are physical experiments. They are big, they're extremely expensive, billions of dollars. So that means when you build these experiments and before you run the experiments there, you actually want to simulate them pretty well, because you don't want to have a situation where you set up very high currents, very high temperatures, and then the whole system melts if you built it for billions of dollars. So you want to have these high fidelity simulations, physics simulations of these systems. They have many input parameters. They take sometimes long to run, which means it would be useful to have a toolkit to help with this optimization and scanning these parameters. And this particular project, where we had collaboration between physics and computer science, led to at least 2 physics papers where I was involved and lots of other physics papers over the years. Then the other application area, and here I illustrated by a sort of schematic on the right here, where there is some binary decisions. You're at time step 0, you can make 2 decisions here, and you're at other time step, you can make 2 decisions. And actually here you end up in a situation where there is no choice left. You can only have 1 possible transition, and here there are still 2. And so this is a very schematic description of some kind of a decision problem. So you have to decide in a few time steps what to do. And then there are some numbers which you don't need to read, which are sort of partial rewards, and you sum up those rewards, and then you may compute the optimal route through this system, that this would be the best way to act in different steps. And then you add probabilities onto this, because usually, even if you decide you want to go up, you may actually end up going down due to other things in the world, like a pandemic or an election or a war or something like that. So you have to have probabilistic computations here. But you can take the expected value of the outputs and still compute what is then called optimal policies. And as I mentioned earlier, uncertainty is very important here. So we actually have a separate paper which basically explores the impact of uncertainty on, in this case, optimal emissions policies. If you want to make decisions about how much to emit, how does it change the situation if you're unsure about if somebody will actually follow? You set a law that you have to change to electric cars. And then it's a question, to what percentage will it actually materialize? And if it's 0%, then of course there is no effect. If it's 100%, it's perfect. But how does it vary in between there? And it's actually not a monotonic function of the probability. So there is actually some maximum somewhere, which is a bit surprising in some settings. So then we explored a little further and wanted to see, can we try to look at responsibility under uncertainty, or importance of different decision steps. And here, if we look back at this figure, when we're at a position where we have no choice, there is no decision power left, then clearly also we can't really have much responsibility left. Somebody has probably screwed up earlier. But that means that if we have at least 2 decisions possible at a time step, and we can compute with the same kind of algorithm the optimal decision and the worst decision. And if we take the difference between those, well, with some normalization, then we can get a feeling for, in different time steps, how important is this step. Because it might very well be the case that we have these two steps, these 2 decisions, these 2 directions to choose, but it turns out that the expected value of both will be the same. That even though it's 2 different choices, if the expected value is the same, then we don't really have any responsibility left. There is no difference in the outcome. So that's an interesting aspect where, without really knowing that much about the system, we can still try to guide the policymaker towards where one probably wants to invest more money in exploring the options. So if there is a particular decision, say time step 3 in this state, which is very, very important to get right, otherwise sort of all hell breaks loose, then we can add extra funding to explore, maybe say some consultants or companies should sort of explore these alternatives better or something. Okay, so this was examples of the 2 application areas. And you can say these 2 are rather different, but there are commonalities. And I want to get to the part where I can talk about a general setting for these. So fusion energy, climate policy are different, but first, real experiments here are either very expensive or impossible. I mean, we don't have planet B. We do an A/B testing, planet A, planet B. We tried different climate options, and then we wait 10 years, and then we see which was best. We take a time travel back, and we implement the best one. I mean, that's clearly not possible in the real world. We might be possible with really big resources to say that, well, this European country implements this tax policy, this one another tax policy, and then hope that everything else is the same, and then try to see what happens. But also there, even if it would be economically and socially feasible, it probably wouldn't, we don't have the time sort of to wait for the result and then implement the results. So it's really important to be able to do numerical simulations here. I should also say, which is not the topic of this talk, but it's also very important that the numerical simulations are done with a model which is close to the real world. because you always have to model the world. You can't really compute with the real world. So, and as what someone famously said, that all models are wrong, but some are useful. So you have to find useful models of the world and then try to simulate it. Anyway, so these numerical simulations are important and hopefully even correct. They have several input parameters. There are different things you can vary, like how much you should invest in your budget year 1, year 2, or how much you should tune the parameters of a fusion reactor design. And then there are also several objectives that you want to minimize. So here it could be in the fusion case, something called the runaway current, the heat load on the wall, the physical stresses on the magnets and so on, because you don't want the system to break when you built it for $1 billion. And the climate side, you want to minimize spending, emissions, unemployment, these kinds of things. And not surprisingly, these would tend not to be minimized with the same parameters. So we'll have to compute some kind of a trade-off between these. So if we abstract one step further towards mathematics here, the object of study that I will talk about throughout the rest of the talk is an expensive black box objective function f, from m real numbers to n real numbers. And the aim is to find approximate minima of this function. And I will explain on these words a bit more. So first, expensive here means that each call to this function could take minutes or hours to evaluate. I mean, it could also take months to evaluate, depending on how big simulation of how high fidelity simulations you got. But the case that we've been working on are minutes to hours. And why is this relevant? Well, it's the black box part. We can only learn about the function by running it. It's not the case that we have a closed form analytical expression and we can explore its properties and its limits and so on. We have basically a simulator, and that's why I call it a black box. So even if we do have the source code, looking at the source code will not give us an intuition for what fusion parameters would be good. It's a source code which simulates the real world, either physics or climate and so on. And it's rather complex. It has lots of time steps. It computes something, but you can't read it off from the source code. So that's what I mean with black box here. And that means that before we start an optimization problem, we are really pretty blank. We know basically nothing. It's like in these kinds of two-dimensional adventure games, you drop into a cave and you don't have a map. You're just sitting in a point. And then when you move around, you start getting one box at a time, expanding a little map around you so you sort of know where you are. A bit similar to that situation. Okay, objective here. It's something we want to minimize. And I put it here as one objective function, but it returns n numbers, could be 3 numbers. So you could also look at it as 3 objectives, 3 different functions. So it returns a triple, but you can look at the first, the second, and the third separately. So, and as I mentioned, there would usually be a trade-off between these different numbers. Function. So this is interesting. So the word function is often used rather sloppily. So something might say that the climate reaction to greenhouse gas emissions is a function of the human activity. So, well, I mean, it's a function in the sense it depends on human activity, but it's not a function in the sense that if we do if we behave in one way, then we know exactly what the effect will be, and we behave in another way, we can compute exactly what it is, because it's a function, if you would say, perhaps of lots and lots of things. It takes the whole world in. So function here is really a mathematical function implemented in the computer, which if you give it a tuple of m real numbers once and compute the result, and you give it again, you will get exactly the same output. So there is no randomness, no stochasticity in the system. It only computes exactly a tuple of outputs. And why is this relevant here? Well, part because it makes the kind of optimization problem is rather different if you have a stochastic function or if it's a deterministic function as here, but also because from the point of view of expensive up here, it means that it really pays off to memorize the results. So if we call the function once, we should save the pair of inputs and outputs and keep it, so that when we learn more and more about the function, we shouldn't have to re-evaluate it on the same inputs. Okay, and then approximate minima. Well, we could say, of course, we want to minimize the function, we want to find the minimum. But the minimum would take infinite compute resources to find the exact minimum. So in practice, we always want to approximate the minimum. And I also say give small values for the objectives, and that's also because they will compete with each other, so we will not be able to minimize them independently of each other. Okay, so in the physics example here, we have basically two control inputs. There are more, but the two that we will vary in the example later, and 4 objectives. So the main inputs here, the 2 main inputs are these 2 gases that are injected. This is a particular numerical experiment. We have a fusion experiment, something goes wrong, we want to cool it down. So we, as Tunde used to say, we want to throw a snowball at the sun. So the sun is, we have this fusion reactor that's a bit like a sun on Earth, and then it's very hot, and then something goes bad, and we want to quickly cool it down so that the machine's inside is not damaged. So we actually make the snowball out of gas, so it has to be cooled to very low temperatures. But that's like the technology behind it. But the thing interesting here that the 2 inputs is the amount of 2 different gases. And usually there is a minimum possible and a maximum possible. So we have an interval in each parameter. So basically a rectangle in some space of the possible inputs. And we want to find the optimal possible output of this function in this rectangle. And objectives I mentioned before, I think it could be things like the currents, the heat load on the wall, and the stresses on the magnets and so on. On the climate side, we have a simpler example. Actually, the one I will show here on the slides later will be a made-up example, just to illustrate the case in a more understandable fashion. Here there are 2 control inputs and 2 objectives, and we can think of the control inputs there as perhaps the budget year 1 and the budget year 2 in some actions to reduce emissions. And the objectives are spending and emissions. And I actually will make spending and emissions relative to some base budgets. So spending 0 doesn't mean it costs nothing. It just means it doesn't cost more than the base. Okay, I should also have mentioned early on that if you have questions, do feel free to ask. Okay, so the first part, that there will now be 2 parts of the talk, the rest. In the first part, we will look at Bayesian optimization and using cost functions. So ideally, so there is a sort of, we would like to compute the full trade-off between the different objectives. But if we have a reasonably easy way of combining them, say that they are equally important, then we can add them up, or we can take the square root of the square of the 2 objectives to get sort of the 2 norm of the pair of outputs and so on. We could try to compute some single value using what is called a cost function, and then do single objective optimization. So why is it called a cost function? Well, it basically sets prices on the different things. So they could be emissions and unemployment and so on. If we translate everything into one currency, that's this cost function. I should note that this is cheating in the sense that we don't, it hides the trade-offs, we don't see them. It's very often used, sometimes well motivated, and I will get back to the case where you really have the trade-off in the second part. But let's look at this one parameter objective version first. So we've published 2 physics papers based on this using Bayesian optimization, which is what I'll spend the next few slides explaining. And this is for the thing when you throw this frozen gases into the hot reactor and try to make it cool down in a controlled way. And there are different technical aspects of how to do this physically. The next few slides, I will try to illustrate Bayesian optimization in a case where it's easy to show on screen. So now suddenly we have not only one output after this cost function applied, but also only one input. M equals N equals 1. So a real-to-real function. So this is step 0. This is when we are dropped into the dungeon and it's completely dark, we don't know anything. So Bayesian optimization is a global optimization method. It can be used to find optima in a certain, in this case, one-dimensional, it's an interval between -2 and +10. And to make it understandable here, I've actually made the black box white. So this blue function here is the truth, the ground truth, the answer. That is the function. But the algorithm doesn't know it. Currently, the algorithm knows nothing about the function, but it's actually sine of x. So it's a very sort of simple example. But we have to have some kind of prior belief about f. If we know completely nothing, then it's not very easy. So here we say, okay, let's assume the function is centered around 0. So the dashed line here is our current best guess of the function. The function is probably always 0. And the red area, that's the 95% confidence interval of the function value. So the function could be anywhere between -2 and +2, anywhere in this interval. No information available. Clearly, this is not a very good start, so we have to evaluate at least one point. So let's do that. Now I just suddenly got this data, but you should remember this is supposed to be done for expensive functions, so it might take an hour until we get here. But after we got that one value, that's the red dots here. At that point, the uncertainty has melted away. We are completely sure about what the output is. Then the uncertainty goes up, so far away on the left or right, we are completely unsure about the function value again. But now the expected value here, the sort of guessed function, is just around 1. So, and the interval has now shifted up from -1 to +3, but otherwise it still has very little information. With only one point, we can only guess a constant function. But we update the knowledge. So this is the posterior after this one. It shows the probability distribution of these functions. I should say also, it has a certain steepness here, which is one of the meta parameters to the Bayesian optimization. We have to assume something about the functions. We have to assume, for example, that it's continuous and has a limited derivative. So you can see basically this is the slope here, which is the maximum derivative we sort of allow. Because otherwise it would be, it would take even longer. Anyway, after a few more point evaluations, this is what we know. The uncertainty in this region has suddenly gone down to very little. Here with more uncertainty, but we got a nice value here, which is the best guess so far for the minimum. And the approximation of the function, the guess, the dashed line, starts being squiggly at least. So it's a better approximation of the sine function. But of course, we have only 3 point evaluations, so we have very little information yet. And if we're looking for the minimum, we can combine the guess of the function, which would indicate that we've already found the minimum, and the uncertainty, which would indicate that perhaps this is a good point to look, because here it's probably, well, it can be the reasonably high probability all the way down here. Uncertainties are enemy here. We want to be able to do a global optimism, which is better than this one. So we have to spread out a bit. Whoops, sorry. There should be one more step. I first wanted to show what happens after 7 steps, but that's the only thing that happens is you start approximating the function better and better. So, and I wanted to mention as well that the point of doing this Bayesian optimization, so taking one point at a time, learning from it, and guessing based on that, is to not do too many function evaluations. Because remember, if it takes an hour per point evaluation, you don't want to do a uniform interval of 100 points from -2 to +10, because then we got 100 hours waiting time. And we can get to basically the same precision after maybe 10 function evaluations if we, after each one, decide to pick a good next point. So that's the main idea of the Bayesian optimization. Okay, so what did we use it for? Well, there is a big simulator called DREAM, or Disruption Runaway Electron Analysis Model, which takes some control inputs. It's a black box. It computes actually 4 different outputs. But it computes more than that, because it computes the trajectory in time and the distribution in space inside the reactor of these parameters. But we take the maximum of certain things and the the time for certain intervals. So we compute some things which are intended to be minimized to be able to protect the reactor from breaking. And then here, as I mentioned, we are in this first part of the talk when I use a cost function called L, which will we normalize these things, because notice they are different dimensions even. This is a current, this is time, this is a, well, actually dimensionless quantity. And they are normalized, and then they are combined together to get one cost. And the idea is that if this cost is minimized, then all of these will be minimized. It's not quite true, but it's a good approximation. But this is the output. I should say that now we have a two-dimensional input space, and the color here indicates good or bad output. So that the output of the cost function is drawn as a color. So almost everything is bad. Red is bad, and blue is good. So this little area here is the area where we want to be. And with the specific cost function, we will get to a particular point, which is the optimum there. So this cost function, as I mentioned, it combines these different things. This parenthesis here says incomplete runs. That's because it's very common when you have this kind of simulators that certain combinations of input parameters will actually make the system either crash or end with an error message saying like unphysical inputs or something like that. I mean, not in this particular case, but you could very well end up at, say, the Kelvin temperature is negative or something like that, something which just cannot happen in reality. And if you end up in that case, then you know that something has gone wrong. And what we do then is we give a big value for the cost function. So we punish this region by it. So we sort of stay away from it a bit. What may not be very visible is that there are little gray dots scattered around. There are around 200 of them here. And those gray dots are the function evaluations. So actually, the only thing we know is the value at those points. The rest is an interpolation. So there are some artifacts of the interpolations. It looks like there's sort of little peaks at these different points, but it's mainly because of the way that the approximation is computed. But it does have a clear sort of valley here. If you look at blue as low and we want to minimize, then this is a region which looks promising. Actually reasonably thin in this direction and sort of high. So yeah, as I said, gray dots are the inputs, and we have found one optimum here at the start. And as I mentioned, for the second part, we want to look into how do we compute the trade-offs between different optima, because this particular cost function gives this optimum. If we would change the cost function in any way, the optimum would move. Perhaps not a lot. It's a little bit hard to guess from just looking at this where it would move. It would probably be somewhere in the blue area here, but it's not obvious. And it would be good for the policymaker in the climate side or the engineers building the experiment or the physics people to know what is the trade-off. Because maybe it's actually the case that certain combinations are more tolerable than the others. Yeah, others may give a better trade-off, that was what I was saying here. Okay, so let's go to the second part of the talk then, where we, I said, first motivate here about what the problem is. So we have a bit of magic hidden in this cost function, which is often based on a weighted sum. So we have the different objectives, we weight them. That's because of the normalization, and then we sort of collect them together. And choosing the relative weights is a difficult problem, which means that actually we have, in some sense, suddenly more parameters here. So we don't really have an optimum. So I say quotes optimum, because for each cost function, we have an optimum. But if we change the cost function, we get another optimum. And that's not very satisfactory. Sort of the optimum here is not a property of the system, of the physics, of the climate. It's a property of the combination of the system and your cost function. So maybe the cost function doesn't have a big effect, but actually in several cases, it does have a reasonably big effect. So it might be important to check this. So mathematically, it could be good to do it, but there are other reasons as well. It's not only a mathematical problem. It could also be an ethical or legal problem. If you're at a company and you're building self-driving cars and you sort of want to compute the lives lost and the money spent, it will be very difficult to convince the lawyers in the company that you can set a price tag for the deaths. They will probably say something, no, there's no such thing as an acceptable death. So all depth has to be 0. And of course, from an engineering point of view, there will always be a risk. I mean, if you actually travel, there will be a risk. Then what we can do is to actually compute both. I mean, we can compute a trade-off curve, which is this Pareto-front, and let the experts decide. So the Pareto-front is then a generalization of the minimum from the one-dimensional case, which is and then explained here. So now we're back at an example. I've simplified it from the physics. So this is actually a constructed example, but the way you think about it is some investment year 1 and year 2 in some climate policy case, and you get some relative emissions and relative spending. So you want to minimize both, but they are not possible to minimize at the same time. This is the rectangle that is the sort of the interval in both parameters that you're allowed to look at. You're supposedly have been told that that's the only reasonable parameters. And at the right-hand side, we so far have an empty grid. So we have evaluated 0 points so far. So no information available. But let's pick a point. The input A here is then 1.5 of year 1 and 1.5 at year 2. And then we compute the function, might take an hour, and we happen to get this point here, which apparently has 2.5 units of spending and 2.5 units of emissions. At this stage, of course, we know a little more about the function. Not very much more. We have to evaluate at least one more point to have some comparison. So let's pick another point, this B here. And now we can start comparing. And here comes the difference to the one-dimensional minimization problem, because we have 2 different ways of measuring how good this is. So in this case, the point B here has a lower emissions, a little bit lower emissions, and much lower spending. So it's clearly beneficial to go to B compared to A. But if we take another point, C here, that is also beneficial to choose in front of A, but it's not at all obvious how to rank B and C relative. So there is no total order here. You can't just decide that B is better than C. B has 2 units of emissions, no spending. C has 2 units of spending, no emissions, as I said before, relative to some base case. And depending on the situation or depending on the stakeholder, you may want one or the other. So somebody who's very much cares for the emissions has one thing, one who's responsible for the budget may have another opinion. So we have just 3 points here, so we probably want to evaluate a little more. So let's take a point D, which happens to come in the middle between B and C. So, okay, that's nice. Then we have a compromise. So notice now that B, D, and C, they are all better than A, but they are actually incomparable internally. So we could say, okay, but let's just add the 2 up. Let's add the emissions. 1 unit of emissions equals 1 unit of spending, in which case all of these 3 would be indistinguishable from the optimization problem's point of view. So if we have a cost function which just adds x1 and x2, then suddenly the system could return any one of these without telling you that there are 3 of them, because I mean they're just completely the same. So that's where we start to see a little bit that what is hidden when you compute one-dimensional optimization instead of a 2-dimensional in this case. And just to illustrate the nonlinearity, so I pick a point here in between A, B, C, and D on the input side, and it computes the point E here, which actually turns out to be better than D. So E doesn't have to be in between those points here, because it's just a nonlinear simulator of something. So, but at this stage, we can throw away D, because now A was bad, but D is also not very good, because we can improve both, we can decrease the spending and we can decrease the emissions compared to D. So B, E, and C are now the sort of best approximation of the Pareto-front, as we will see later. Okay, I will not try to throw darts at this one anymore. I will just summarize this. So here is a little bit like the blue curve a while ago. This is try to go and make the black box white. So here I've actually done something we cannot do. I've computed sort of infinitely many points just to show that very often you can draw these at least approximate curves through these. So each of these curves is one where we fix one of the controls, the investment year 1, and then we vary the year 2, 1, or the opposite. So for example, you can here see that D and C are on the same curve here, and D seems to be the one with the lowest spending, and C is the one with the lowest emissions on this particular curve. And then E lies on the curve which sort of goes there, and B and D are also on another one of the curves which are sort of orthogonals. And I'm not sure if you can imagine this geometrically, because in the bottom we have a two-dimensional input space and two-dimensional output space. So the function is a four-dimensional thing. So we can't really draw it. But the sort of net you can see here, the sort of the bag, is the image of a regular grid in the input space. So that's sort of warped, something like this. So it's bent and warped so that these points on the edge, those ones who come as close as possible to the origin, those are all incomparable, but all sort of optimal points. And that's what I've summarized here. So the yellow curve here is the Pareto-front. Mathematically, it's the ideal thing that you compute infinitely many points, and then you pick all the ones which are at sort of as close as you get to the origin. And then you can deliver this to the policymaker and say, okay, pick your choice of, pick your poison, sort of. I mean, how much emissions do you want to have? How much spending do you want to have? You can translate between them with the trade-off function here. And the aim is then to present the Pareto-front to the policymaker. Or, I mean, realistically, you wouldn't present the Pareto-front, but you can't compute it. You would present a few alternatives like B and E and C here, and say that those are possible cases you can get by choosing these particular input parameters. Okay, then just two more slides on what we actually do to find the Pareto-front. So remember, we started with the rectangle in the input space. And that's the first little figure here. We start from a rectangular cell in the control space. That's the minimum and maximum of the two parameters. Well, it could be multidimensional, but here let's stick to two. We evaluate the function at all the four corners. And based on the input, we decide on splitting it. In this case, we split it sort of in this direction. And then we continue recursively in those cells which map to the Pareto-front. And I say Pareto-front here, I mean the approximate Pareto-front, because at every point in this stepwise refinement, we will have a very crude but still approximate Pareto-front. And then we try to sort of refine it. So this case, it's split in that direction and then the other direction, and then after a while, maybe all the optimal points are in this little box.
You've split it in one place in each step here.
Yes, yeah, I didn't have the energy to draw, but it does split in multiple places. Yes, so we do a bit of parallel search, you could say. So because it's also the case, as we could perhaps see from the sine function, there could very well be disjoint regions for minima. So it doesn't have to be the Pareto-front doesn't have to be one continuous curve. It could be curved segments.
It certainly doesn't have to be all in one cell.
No, definitely not in one thing. Exactly. So anyway, what does this look like? So this is then, we call it adaptive mesh refinement. So we start with the cell, we split it recursively down. And this is a zoomed in view of the fusion case we had before. So remember, there was sort of a blue valley, and this might be difficult to remember, but at that point we had 5 orders of magnitude, where it was like from 17 to 22, I think was the scale on that axis. And now I've just from 21.9 to 22.9. So it's a very narrow rectangle actually in the previous figure, because the blue valley was rather narrow. So I narrowed it down and sort of zoomed into that one. And then the other direction, it's a little bit of a zoom, but only half of the diagram. And then we've done this splitting, and you might see these black dots here. There are all the sort of corners of these cells. So down here, there's a rather big cell, but here there are very, very small cells. This is after around 600 point evaluations. And we also colored, we first, as we don't use the cost function here, we have a separate graph for one of the terms and a separate graph for one of the other terms in this. I only picked 2 of the 4 outputs here. And it's not very visible here, perhaps, but the red part is bad for this objective. So this is sort of, this is the good direction, bad to good direction here. And here it's the opposite direction. So there really is a trade-off in this local region. And the nice thing is then that we got a pretty continuous looking Pareto-front. So every little gray dot over here is a point evaluation which has been dominated by one of the points on the Pareto-front. Dominated in the sense that you can improve both the one dimension, but one the objective and the other objective by moving to the Pareto-front. There's some interesting geometry. It seems like there's like one part and then there is another little part. I'm not sure what to read out of these things, but it's fun to see that we can read off this, and due to the coloring, you can also see where in the input space these different parts of the Pareto-fronts map to. Okay. This is summarizing it. We've got some examples from fusion energy, from climate impact research. Part one was about basin optimization, where you sort of combine the different objectives by a particular cost function, which is a research project in itself, to choose a good cost function and make sure that it actually gives reasonable outputs. And part two, trying to see if we drop this cost function part and want to compute the actual Pareto-front to capture the trade-off between the different objectives, then we have this future and ongoing research to actually compute this Pareto-front and apply it also in the climate impact decision side. So we've done several papers on the climate side on single objective optimization, but we have not yet done a case study with multiple objectives there. What is hidden here is that we had actually 4 objectives in the future case, and I only drawn 2. And you can guess why, because with 2, I get the curve. With 3, I get the plane in 3 dimensions. And with 4, I get a 3-dimensional manifold in 4 space. So yeah, my head starts hurting at that point. So I'm not quite sure even how to visualize it. There are usually some projections into different pairs of 2 dimensions. But the interesting thing is that the algorithm seems to be reasonably scalable when it comes to splitting the cells and doing this, similar to basin optimization, but in a little bit more controlled fashion, at least in the sense that we've written the code and we haven't just taken it offline. If you're interested in this kind of stuff, there is more on the link here, which is a course called Functional Programming Climate Impact Research. That's more on the climate side that we were teaching in the spring. It's about 10 weeks of lectures and some exercises and hand-ins and so on. And we can do it again next spring, for example, if somebody is interested. We did it both locally and on Zoom last time, so that's probably doable if there is interest. And otherwise, questions?
Thank you very much, Patrick. There's plenty of time for questions. So you'll make the slides available.
Oh yeah, I should upload them, yes.
So we can put them on the Kellogg event page.
Yeah.
I'm not sure how long that will last actually. We can put them somewhere anyway. So
yeah.
So that's a link to the course materials.
Yes, exactly. And I mean, if you're curious, that's the content. Anyway. And I can put a blog post. I got the homepage with some blog posts, so I can put it might be more stable than the event page.
Yes. I'm not sure what we do with our event pages when the events are passed.
Yeah.
So you showed us these 2 charts here and the 2-dimensional surface that you want to, area that you want to. So for more dimensions, it's difficult to visualize what the right thing to do is. You could do the experiments and get some numbers and produce a table. Is that table useful to the plasma physicists, or do they need to put on their augmented reality goggles and navigate around a visualization space?
I think very often there is a certain kind of look at like a triangular matrix version when you have like one plot for each pair of dimensions. So you sort of project it onto 2 dimensions at a time.
Yes.
So that's one way of visualizing it. It's not perfect because you smash lots of things on top of each other. So I'm not very good at multi-dimensional visualization, so I don't know. There's probably ideas and results out there. But
I mean, it's a big thing in all sorts of areas. I mean, even just visualizing code bases.
But yeah, I do think that sort of being able to turn and sort of looking at, so maybe not just because in a paper you would do this sort of triangular matrix kind of graphs with this, but I think if you actually want to explore the data, you probably want to have some sliders for deciding which projection you want, and not just axis projections, but any sort of kind of direction. Yeah, you want to rotate the 4-dimensional cube. But I haven't tried. My forte is not the graphics programming.
No, it's an interesting problem.
Yeah.
More questions? Is there anything online, Max? No. Thinking about the multi-objective optimizations and the costs, and we do that in all sorts of areas in policy. And I'm thinking in particular about the National Health Service here in the UK. They have information about lots of illnesses and lots of treatments, and some of them are rather expensive, and they only have a limited budget, and they have to decide which ones are worth paying for and which ones they're not going to pay for. So they do smash that down to a rather crude, basically a financial value on quality adjusted life years. So they'll pay for a certain.
So a rather complex, but still a cost function.
There's still a cost function, right? Yeah. So somehow they decide that this particular treatment, although it costs £20,000 a year, it'll give you another year of life, and therefore it's worth the taxpayer as a whole paying for. This one, even if it costs a bit less, will only give you a few extra weeks, and therefore is not worth paying for. Have you contemplated talking to the?
No, I haven't really. And I mean, lots of people in economy, these Pareto-fronts are very common, but then it's very often very many dimensions. So you have a number of agents, and each one has a welfare function or sort of a reward function, and all of those. I mean, it's as many objectives as there are people in the system.
Right, stakeholders, yes.
Stakeholders, and that's. I don't even know how to think about the price system there, but I guess it's one of the motivations why prices and cost functions are there. I guess because it's difficult, and also I should mention that it becomes when you sort of increase the dimensionality, it becomes very sparse.
Yes.
So you would need very many runs to get this surface in the multi-dimensional space. So that would probably, you would, even if you had like 40 objectives, you would probably want to group them into 10, and I have 4. So that might be manageable.
Right.
So you would have 4 cost functions and 10 arguments each.
I have more questions. I was thinking, so the way you do the experiment, you run one and then use that information to decide which one to run next.
Yeah.
Maybe you run 4 on the corners and then use that information. So then you have a linear dependency between all the experiments. You can't run the second one until you've worked out what the answer you get back from the first one.
Yeah.
But I mean, if you had several actual tokamaks to do the experiments on, you should run them in parallel. If you don't, but if you've got several computers, you can do the simulations in parallel.
Yeah.
So you might not wait for the results of the first experiment before deciding the second one, and you do some kind of interleaving of these things. Does that change the way you would choose the?
No, I mean there's another trade-off in the algorithm, but usually we do spawn like 4 computations at once or something like that. But it does mean that you would potentially have to do more runs, but if you can do them parallel at the same calendar time, that's probably perfect. But it's I mean, if you would have, I mean, it's the problem at the basis is perhaps embarrassing in parallel. You could just run the evaluator on 1 million cores, and then get a sort of lots of numbers, but it would be, I guess, very energy costly to do that. So you want to, but I don't know what size of bunches could be good.
Right.
But I mean, for pragmatic reasons, we did 4 on the computer because it could run 4 simulations at once. Otherwise, it would sort of blank. But we didn't use it try it on a cluster or anything like that. But clearly, if you're in a real setting with real big money and so on, you probably want like perhaps 100 runs at the same time. Or
Well,
something
if
like
you're
that.
trying to decide on lockdown policies for pandemics and it's really time critical, you might do more simulations at once. Oh, questions, good.
Yeah. What's the benefit of using functional programming versus another programmatic approach?
Well, for me, it's mainly to make sure that we understand what's happening. So my brain is not well wired to destructive updates. So if you actually start changing the state, that's always complicated. So if I have mathematical functions, I know exactly how they behave, and you can probably prove correctness and things like that. So that would be one argument. The other is you got this algebra programming I mentioned about earlier. So you can really sort of simplify and compute and change the programs. For example, this kind of trade-off between the parallelism and the sequentiality, you could probably with some combinators switch back and forth between these versions without having to do lots of complicated transformations of your code. And I feel that the way, at least the way I've been taught programming, combinators, libraries, and configurations is easier with functional programming. I'm not sure if there is a user study that confirms that, but for me, it's definitely true.
Congratulations on getting through 1 hour without mentioning AI.
Oh, okay, yeah, it was only 45 minutes, so it comes up now. So.
Is there not a role for AI here?
Well, AI is sort of orthogonal to this question, but I mean, in one sense, you could say an AI system is an interpolation system. You have lots of points of inputs and outputs, and then you try to make a function which approximates that. And that's of course useful. For example, if you've run your 100 simulations or 600 simulations, maybe you want to train an AI on this and then not run the simulator an hour per point, but just get it to basically interpolate between the points.
But you're giving instructions to an AI, and I think that's forbidden. The AI has to learn.
No, but the AI always has the data instructions in the sense it has to get input. I mean, it has to get data to learn from. And what I'm saying is the input-output pairs of this simulator is suitable data for training an AI, for example. If you want to, because the thing is that if you want to, very often we've computed this particular setting, and then there is another parameter which we didn't vary in the experiment, which we also actually do want to vary. Then maybe we want to not run the simulator again for all of these points. We want to sort of just transport the results a bit, and maybe we can learn the behavior and make a fast and loose computation of the result, which approximates the real run. And then we can make maybe some simulations, sort of fake simulations using the AI. And then now and then go down to the real simulator and check, are we actually close to what we wanted? Because the main problem with the AI is we sort of lose the feeling for what is reasonable. I mean, you can give a number, but we don't really know why or exactly how it gives the number. So
that's going the entirely opposite question of why use verified programming for this kind of thing.
Yeah. So yes.
Back to the question here from Jonathan. You talk about functions taking hours to run. Is it actually realistic? What function simulations have you encountered that take such a long time?
Well, but is any of these physics simulations with sufficiently high precision? So I mean, when that black box, I'm not re-implementing in the functional language. I'm just calling it. So that black box is a combination of Python and C++ in this dream simulator. And that one basically solves a bunch of coupled differential equations with lots of machinery, step by step through time. Well, yeah, depending on the setting, the fastest you can get is 4, but that's like a one-dimensional setting, and it could be multiple hours. And there are also, this is still the whole dream simulator that we're using. That's still a rather crude representation of a tokamak reactor. So there are some other groups who work on supercomputers, and then it could be a month before you get your output. So
Still cheaper than building an iron reactor.
still cheaper than building a billion-dollar reactor and trying if it works. Yeah, sorry, this was, I suppose I should look at the chats.
No, Max is doing that, it's fine.
Yeah.
It is about time. I've got one last question. There was a question about AI. Well, I've got a comment, question about AI. Calogians will know that our current president, Jonathan Mickey, is the son of Donald Mickey, who was a pioneer in AI in Edinburgh in the 1960s. Sort of game playing and that kind of thing. But he also, you mentioned memo functions. Donald Mickey invented the idea of memo functions. So these are functions that you call, you give it an input, it gives you an output, and remembers the one it gave you. And next time you call it with exactly the same input, it gives you back the output without recomputing it, which is very useful when it's an expensive function. So that's an invention by Donald Mickey in 1968.
Okay.
Donald's photo is in the corridor out there. He, among others, was working at Bletchley Park in the war on code breaking. So there's a long-standing connection there. But let's thank Patrick for a very interesting talk. And yeah, if you have any more questions,
I'm here.
See if there's something right away.